pretty much all the companies are designing smartphones, cell phones, have some kinds of tools that are like what I'm going to describe to figure out how long it takes to do a task on a phone. What does the user have to read? Which keys do they have to press? How long does it take to do it? Another example has been work on flight deck. Here's a flight management system from 777. There are various things that the pilots have to do to fly that aircraft. The steps and tasks the user has to perform are pretty well identified. So the question is, can we figure out how long it's going to take? So all this relates to something called GOMS. This is GOMS in some sense. This is GOMS in Switzerland, but we're probably not talking about that. So what we're talking about is GOMS, which is short for Goals, Operators, Methods, and Selection Rules. This is on page 23-4. And so this is both sort of a calculation method and a way of thinking about how do we analyze primarily cognitive activities. GOMS stands for 4 essential elements of the modeling approach. The first is goals. So you need to think about what is the person trying to do at each step. And I want to really emphasize focusing on what the user goals are at each step. Okay, the person has to do this. Well, what does that mean? What's the sub-goals below that? What are the sub-goals? The tendency is for people to go right to, oh, let me just look up the numbers in the table and start. That doesn't work well as soon as the problem gets complicated. So I really want to focus in these analyses on thinking about what the goals are, being explicit in identifying them. Then operators. So what are the things that a person can do? Press keys, think, search for things, and so forth. And how long does each of those elements take? Methods. How does the person do the task? And this is really important. You may recall earlier that I said a task is a goal plus a method. So for example, if I use an automotive navigation system, one task might be to find an address by to find a destination by entering the street address. That's different than finding a destination by, for example, entering a point of interest, because the steps are different. So if I change the steps, I change the method, and therefore I've changed the task. Selection rules. How do I decide at each step what to do? So GOMS is these characteristics rolled together. This approach is not one simple analysis procedures, but a collection of them. And what I'm going to do is try and talk about the centrality of all these procedures. So first is something called the model human processor. And this is really sort of the original piece of GOMS. This is the most complicated part. And it's sufficiently complicated that I'm not going to talk about it first. I'm going to talk about it second. Because if I cover these details first, you'll just be overwhelmed. Right? Then there's the keystroke-level model, which is basically a simplification of it. It was originally developed for office-type work, but could be used for pretty much anything, as you'll see. And it's literally identifying on a keystroke-by-keystroke basis what the person does. And what's unique about the keystroke-level model is it really starts to focus on what are the cognitive activities. So with that, let's go to the table that starts to talk about the keystroke-level model. And let me talk about the task and this table. So the first point I want to emphasize is the keystroke-level model assumes that the task is a routine cognitive activity. And by that, we mean the person basically knows what to do. If it's, oh, I have to look at the screen, I have to think for a long time to kind of read everything and figure out what's going on, it's not a task. It's not a tool that's going to work very well for that situation. It's like, if we're looking at sort of the first time a person figuring it out, it just doesn't work. And the reason is we don't know what the person's doing, really. Right? We could describe it at some kind of high level. They're trying to figure it out. But can we precisely say exactly what the person's doing? The answer is often no. Well, if we can't precisely say what they're doing, how can we estimate how long it's going to take? All right, so the other assumption is that keystroke-level model makes is there are no mistakes. That's unrealistic. For a lot of these tasks that we use keystroke-level model to analyze, error rates are typically sometimes as high as 25%. They do some part of it wrong. All right, well, that's not a killer. The solution is, okay, a person does this, and we think at this step they're going to make a mistake. If they make a mistake, what are the steps that they go through, and what are the steps that they go through to correct? Right? So I can still estimate what they're going to do. Now, how do I estimate average time in that case. Here's the time for a correct. Here's the time for an error. The error probability is such and such. The mean time is this one plus some weighted average of that one. I can still calculate task times. It just becomes more complicated when there are more and more error paths, that there are more and more calculations you have to make. So what we tend to do is say, yeah, there's so many error paths in some situations. It's not worth calculating. Let's just calculate the time for an expert and put in some adjustment factor to allow for errors. And so we can still get a useful number.
Well, is it a weighted average or is it just a regular?
It would be a weighted average. Weighted average based on the probability of an error. And the probability, in fact, of every error. So you can see you get better and better estimates by looking at more and more error cases. All right, but now it's taking more time to do the calculation. So it's kind of a judgment call about how good a number you need. All right, with that, let's go to the data on the table behind me. So the most common action is pressing a key, pressing a button. How long does that take? Well, these numbers were determined by looking at how fast people type. So this is assuming a person kind of knows what to do and they're just banging away at the numbers. Well, how are typing rates converted into these task times? If you look at the English language, the average word length is about 5 characters plus a space between words. Right? So basically what you do is you take the typing rate and divide by, in words per minute, divide by 6, right? 6 characters per word, word plus space, convert from minutes to seconds, and that's where these numbers come from. And so therefore, you have to think when a person is asked to press a key, what is it most like? Is it like they just sort of typing away? Or is it a situation where, all right, I got to look, I have to press this key and this key and this key. And that's more like one of these cases of random numbers or complex keys, right? So you have to make a decision when you start out by saying, who is my user? How much skill do they have? And how quickly do they type if they're asked to type? Right? And this typing applies pretty much to, I got a long stream of text. If it's entering individual numbers, oh, okay, I have to enter my social security number. It's not like they're typing, is it? It's much slower, and so you would use times like this, and it's a judgment. Next number is pointing with a mouse. So when I talked about controls, I talked about the Card, Moran, and Burr study, right, where people had, the undergraduate students had text on a screen, they use a mouse to select. We know from what Rich talked about from Fitts' law that actually the time to select using a mouse is a rather complicated equation, isn't it? Log to the base 2 of 2a over w and some constants. Well, we could actually, for every selection that a person does with a mouse, we could calculate the Fitts' law value. But what they found is for a wide variety of things that people would select on a screen with a mouse, on average, it takes about 1.1 seconds. So we could come up with a better number by measuring A and W, meaning the amplitude of the movement and the target width for every case. But we could just say, on average, it's about 1.1 seconds. So again, there are more precise methods you could use. But if you want to come up with an answer fairly quickly, just call it 1.1. Realizing that some values will be larger than that, some will be smaller than that, but they'll average out. And it may not be worth the effort to come up with a more precise value. It's your call. Home. That comes from that same experiment. And homing is, I'm going from the keyboard to a device, or from the device back to the keyboard. And it takes about 0.4 of a second. If you remember the experiment in great detail, for things that are fixed, it might take a little less, like a joystick or cursor keys. But 0.4 of a second is a pretty reasonable number. The drawing data I almost never use. It's in there, but nobody really uses it that often, so I'll skip over it. Next is the time to mentally prepare. So in some sense, this says that all decisions a person makes take, on average, 1.35 seconds. Do you believe that? I don't. Right? It's a number. It's a reasonable estimate for these kinds of activities where, like, okay, I type something. Oh, I have to think about which item I select in this menu. All right, I figured out what I need to select. Now I go and press a key or make some kind of action. And other studies have picked other numbers, and some people have come up with more complicated ways to determine this. 1.35 seconds is probably as good a number as any to use. Scan. So scan comes from some work that Judy Olson did. And the scanning task was, I got a spreadsheet, an Excel spreadsheet on the screen. I got to find a cell. Are all scanning tasks like that? No, but that's probably a reasonable approximation of all the kinds of things that people do. And last is that invariably you're working with a system, right? I type something in, and I have to wait for the website to go out and get some information and put it up on the screen, right? I click on a menu, and it takes some time for the menu to appear. So the system response times are empirically determined or computed for a particular situation. And you literally sit there and, for example, you might the easiest way to do it is videotape it. You videotape the system, and then you simply count how many frames it takes. And in the United States, in US, video update rates are how many times per second? That's film, is 24 frames a second. It could be either 60 frames a second or 30 frames per second, right? Depending upon your device. So if you know that, each frame is either a 30th or a 60th of a second. You videotape it, you count frames, and you know how long it takes. And you don't need it perfectly because you're now talking about sub-second times, but these are all much larger than that, right? So as long as you're reasonably close, you're good enough. All right, so with that, let's look at a simple example. So let's imagine I was going to take a file that I had on the screen, right, an icon, and I want to drag it to the trash. What are the steps I would go through? Don't worry about the elements in the keystroke-level model. At a higher level, what are the steps that I need to go through? All right, so I need to get my hand on the mouse.
Will you find where the icon is?
All right, so I need to look at the screen.
Click on the mouse.
Then I need to click on the mouse. Then what do I need to do?
Drag the trash in.
Find the trash first.
Right, so I need to.
You need to move
So
the
you don't.
cursor to
So
the-
all right.
to the-
That's a good
Use
point.
that.
So one of the points is it's really easy to forget what's the initial point, right? So one of the questions is, where does the cursor start, right? Does the cursor start on the icon that I'm willing to drag, or is it somewhere else, and there I have to move it? You see my point? Most likely, probably the cursor's not there, right? So in which case, I then have to go through an operation to drag the cursor to the object, to the icon that I want to deal with, right? Then what do I do? Click on it, right? Then what do I do? Find the trash can, right? Drag it to the trash can, release the mouse. Do you get the idea? That's the level of analysis that I would perform. Now the question is, how do I think about that at a higher level of goals, right? And so you might say the first goal is to get the cursor on the icon I'm dealing with, right? And the second is to drag it to the trash. Now, it's a really simple task, but this notion of thinking about the higher levels and then decomposing it is actually very useful. Now, can you see if I've talked about it that way, I could then go to this table and look up all those things, and I could tell you how long that task takes. Now, that was a very simple task. I mean, artificially simple, but I did it because I wanted you to understand what the process is of using this tool.